Okay, guys, in this one, I want to think a little bit more about cannabinoid receptors and their role in obesity and what do they have to do with SEA, stearoylethanolamide, which I've been talking about quite a bit. You can see on the diagram here, we have two cannabinoid receptors, and these receptors are, of course, triggered by compounds in cannabis, famously, like THC. And we have two kinds of receptors called CB1 and CB2. And you can see that not only are they in your brain, as you famously know, which is why people smoke cannabis to get high, but they also have receptors in your skeletal muscle, in your liver, and these have huge effects metabolically, and that's why we're interested in them for this series. And specifically, we're very interested in the CB1 receptor, and you'll see why. We have two well-known what are called endocannabinoids. So these are compounds that our body makes that activate the CB1 receptor. And you can see they're called 2-AG and AEA. And you'll notice they both start with an A, right? AG and AEA. And the A in both of those cases stands for arachidonic. Arachidonic means basically it comes from arachidonic acid, which means that it comes from linoleic acid. It comes from things like soybean oil. It comes from seed oils. And it also relies on the enzyme delta-6 desaturase, which is the limiting enzyme in converting linoleic acid from your food into arachidonic acid so that it can be used to make these endocannabinoids. So if you're worried about producing too many endocannabinoids, and you should be, of course, one of the things you can do is stop eating seed oils and stop consuming omega-6 fats, but it doesn't end there. So let's continue to dig in. We have a system. This is one of the systems we have for producing endocannabinoids. This is specifically how we produce AEA, which is arachidonolethanolamide. So these are our membranes, and any of our membranes can do this. This happens in adipose tissue. This is phosphatidylcholine, and this is phosphatidylethanolamine. Ethanolamine is a complicated word, but it's just this little molecule stuck on the end of the phosphatidylethanolamine. It's literally ethanol, the molecule ethanol, with an amine group stuck on it, which is just a nitrogen, really. Ethanolamine is actually found in space. It was probably just a simple molecule that was in the oceans at the beginnings of life, and so it was a useful thing to use in some of this membrane biochemistry. And so what happens is we have these enzymes, NAT and PLD and FAAH, and what they're doing is they're transferring fats from phosphatidylcholine onto this phosphatidylethanolamine, and it gets released. And when that happens, it winds up in the bloodstream as this fat plus this ethanolamide from the phosphatidylethanolamide gets stuck on there. And this, when it's in the bloodstream, becomes a signaling molecule. So this one's called OEA, oleoil, meaning from oleic acid, meaning from the monounsaturated fat that's in olive oil. If it's SEA, that means stearoylethanolamide, stearoyl meaning it's made with stearic acid, which is the 18-chain saturated fat. And AEA means it's arachidonic, which means it's made with the 20-carbon, highly unsaturated fat, arachidonic acid, which is made from oleic acid that you get in your food. And all of these things are broken down by an enzyme known as FAAH, right? And so the circulating levels of this are controlled by these enzymes that produce it, and largely, and perhaps more importantly, this enzyme FAAH that breaks it down. And so if you can produce a lot of this FAAH, if it's very active, you'll break down these circulating endocannabinoids. You won't have as many. And I should say that of these ethanolamides, the only one that actively triggers the CB1 receptor is AEA, the one made with arachidonic acid. And so this paper shows that indeed our endocannabinoid system becomes dysregulated in obesity. And you can see here's that enzyme FAAH, which breaks down AEA and OEA and SEA and the other kind of endocannabinoids. And you can see that in the visceral tissue of obese humans, they make a lot less of this enzyme that breaks down AEA and OEA. And so those things tend to rise in obesity. Furthermore, this is 2-AG. This is the other endocannabinoid. So this is kind of controlled by a different system, but it also rises in obesity. So in obesity, you have a lot of activation of that CB1 receptor. And we actually know that this is causal. This is a drug called rimonabant. And this is a human trial, a human weight loss trial. What rimonabant does is it blocks the CB1 receptor. So rimonabant prevents AEA and 2-AG from activating the cannabinoid receptors. You know, famously, if you trigger those cannabinoid receptors, it gives you the munchies, right? Cannabis gives you the munchies. I'm going to show evidence that the CB1 receptor does a lot more than just regulate appetite. It also regulates your metabolic rate. In this case, you see the open circles here. People were told to consume 600 calories below what it was determined should be their kind of normal metabolic rate. And they were told to also exercise more. So this is the classic eat less, move more, you'll lose weight strategy. And you can see that worked a little bit for about 12 weeks or so until the people's metabolisms realized what was happening and they were eating less calories. And of course, their metabolic rate slowed down. And the weight loss stalls at around 5 pounds of total weight loss. If they had, of course, maintained an actual 600 calorie deficit over the first year of this experiment, they should have lost about 600 pounds. In fact, they lost 5 pounds. So that is how well the standard, eat less, move more strategy works in real people. These groups, this group here and the triangles, the black triangles, given the same advice, but a low dose of rimonabant. So now they have less CB. They're trying to eat less and move more, and they have less CB1 activity. And you can see that close to doubled their weight loss. And of course, here in the black squares, these were given high dose rimonabant. So they have very low CB1 activity. They have very low endocannabinoid activating those cannabinoid receptors. And they lost about 20 pounds within the first 36 weeks of the study, and they kept that weight off. Conversely, we could look at this paper. These are mice. The mice in the solid shapes up here. These groups of mice both lack FAAH, which, if you remember, FAAH was the enzyme that breaks down AEA and the other ethanolamides. In these mice that can't break down those endocannabinoids, they become obese. You can see the mice in the black squares here. So these are mice that can't break down endocannabinoids on a low-fat diet, and they are actually more obese than mice on the high-fat diet, which is normally very good at fattening up mice. The ones on the high-fat diet that can't break down endocannabinoids, of course, are significantly fatter than all of the other groups of mice. But if you look down here, the two groups of mice with the squares, so this is whether or not they are on FAAH. They ate the exact same number of calories. So you see the open squares here and the closed squares here. These mice ate the same number of calories. And so we can't say that the reason that these mice are fatter is that the endocannabinoids built up and they got the munchies and they overate. They didn't. There's a metabolic difference between these groups of mice. And this paper also pointed out that the weight of the evidence is that this is talking about rimonabant again. This is talking about blocking the CB1 receptor. And it says that weight reduction under these conditions, meaning with rimonabant, is only partly promoted by decreased food intake. And so, again, you're seeing that in addition to the munchies, in addition to appetite regulation, there's some very real metabolic control being enacted at these CB1 receptors. So in this study, they looked at the differences in ethanolamide concentration in the plasma of either non-diabetic but obese black women and diabetic black women, and what are the changes that happen as women go from obese but non-diabetic to diabetic. And so you can see as these women go from obese to diabetic, every one of these ethanolamides go higher with the exception of stearoylethanolamide. And that's always interesting because if you're looking for the kind of master controller, you want to see the one that's regulated differently from the others, which of these kids is doing its own thing, kind of a question. And so then the question becomes, why is stearoylethanolamide being controlled differently? And I suspect that it's because if you look at what happened, so this is in pregnant women, some of whom have normal glycemic control, some of whom have impaired glycemic control, and some of them who have full-blown gestational diabetes. And this is how they separate out in the third trimester. And none of these changes are due to diet. These changes are all due to internal issues in the women. And so you can see with normal glucose tolerance, women have 18.5% of their circulating fats are stearic acid. As they become impaired glucose tolerance, that drops to 17.2%. And if they get gestational diabetes, those stearic acid levels drop to 15.7, and conversely, oleic acid levels go the other way. They go from 24.5 up to 27.1. And so this is the ratio of oleic to stearic acid. In normal glucose tolerance, it's 1.3. In gestational diabetes, it's all the way up to 1.7. And most of these other things don't really change super dramatically. You can see the linoleic acid doesn't change at all in gestational diabetes. The things that change specifically are that stearic acid drops and monounsaturated fats, and especially oleic acid, increase. This is just a study in mice that shows that indeed circulating levels of SEA are related to adipose levels of stearic acid. So as stearic acid drops in the body, you produce less circulating SEA. So that's my assumption as to why women who become diabetic, all of the EAs, the OEA and the AEA, etc., are going up because it's likely that FAH levels are decreasing. They're less able to break down those circulating cannabinoids. The cannabinoids are building up, but they're making less SEA because they have less stearic acid in their body tissues. And so this is from the same paper looking at obese versus diabetic black females. And there's a really interesting data point here. This little blue square that I drew the blue arrow to. If you follow this triangle up here, these are correlation scores between all these different things that they looked at in the obese, not diabetic population. And what they show, if you follow these lines up, this is 2AG on one axis and it's SEA on the other axis. And so what that says is that in obese but not diabetic black women, SEA and 2AG are inversely related. So when SEA goes up, 2AG goes down. Or conversely, if FCA goes down, 2AG goes up. And if you look at all the other metabolites that are negatively correlated with 2AG, which is, of course, the other endocannabinoid other than AEA that activates the CB1 receptor. And if you look for other things that are inversely correlated with 2AG, there aren't any. And so you see that SEA is behaving differently from all the other EAs, all the other ethanolamides, and it's also behaving oppositely to 2AG. And so that sets it up, right, to be a very interesting character in all of this. This paper is another really interesting look at SEA. It's from all the way back in 2002. This is in rat glial cells, so these are brain cells, What the paper shows is that SEA has a binding site in these brain cells, and this is the CB1 receptor. This is what AEA and 2AG are connecting to, and they're activating this thing called nitric oxide synthase. SEA is doing the exact opposite. SEA is blocking the activation of nitric oxide synthase. So SEA has its receptor, and AEA and 2AG have their receptor, and they're having a very opposite activity in these brain cells. And in the abstract, they conclude it seems noteworthy that degradation and pro-apoptotic activity of SEA are regulated by nitric oxide in a way opposite to that reported for AEA. And so in these rat brain cells, SEA is acting exactly opposite of AEA and 2AG. They also pointed out in that same paper that 2AG decreases adenylate cyclase activity by 70%, and SEA does not. So adenylate cyclase is actually the enzyme that makes cyclic AMP, often seen as little c, big AMP, or they call it CAMP. And that is one of the primary activators of AMP kinase. And AMP kinase is a hugely important metabolic regulator. And if you have overactive CB1 receptor activity, you turn off AMP kinase. So remember when I showed you the mice that couldn't make FAAH, and that means they would have a buildup of AEA and they would have an overactive CB1 receptor, and how much fatter they were than the other mice, despite the fact that they'd consume the same number of calories. That's probably because if you have an overactive CB1 receptor, it shuts down your ability to activate AMP kinase. This just shows rat muscle tissue, and the ones in black were given an AMP kinase activator. And you can see that in rats with activated AMP kinase, those tissues burned more than twice as much glucose, and they also burned 25 or 30% more fat. And so AMP kinase allows you to burn both glucose and fat. It is extraordinarily important. You don't want your CB1 receptors to be turning off your AMP kinase. Furthermore, this paper is very important. This is about FAAH. This is the enzyme that breaks down those endocannabinoids, and so you're not overactivating that CB1 receptor. And what they showed is that monounsaturated fats bind to and directly inactivate FAAH, the enzyme that breaks down the endocannabinoids. And so you could see these guys were given a high-fat diet, and you can see what happens is the ratio of oleic to stearic acid in these mice massively increases when they're given the high-fat diet. Now, what did we see in the women when they transition from obese to diabetic? You see a large increase in the ratio of oleic to stearic acid, right? And so in this case, when that activity level goes up, the activity levels of FAAH, the enzyme that breaks down the endocannabinoids, drops. When that happens, AEA, the levels of the endocannabinoid rise, and the mice become insulin resistant. If you give them, and this is what the striped line is, if you give them an SCD1 inhibitor, something that doesn't allow them to convert their stearic acid to oleic acid, what happens is you don't have this big rise in oleic acid. FAAH activity stays normal. AEA activity stays normal. And you don't have nearly the increase in insulin resistance caused by the high-fat diet. And so we can say that the rise in these monounsaturated fats blocking that FAAH receptor and allowing this buildup of endocannabinoids is one of the things that causes the transition to insulin resistance. So I've just added that to this little diagram from this paper because if you look what happens in these glial cells, they also have these transporters that can bring SAE into the cell and can bring AEA and 2AG into the cell. And once they get brought into the cell here, here's that FAAH, and they get broken down into the fat, and that's the ethanolamide. safely, but oleic acid is blocking this breakdown process, right? And so if there's too much oleic acid around, you're going to block down that breakdown process. But of course, it goes one more step even. So they also looked at SEA and its effect on FAAH activity. And what they found is that SEA actually increases the FAAH activity. So SEA increases the ability to break down those endocannabinoids and get out of that overactive CB1 receptor. And so I drew that in. And so you have this direct battle between oleic acid and SEA over the activity levels of FAAH. And that, again, the FAAH is the enzyme that breaks down those endocannabinoids. So basically, SEA and oleic acid are locked in this battle over AEA levels, the endocannabinoid AEA. And lastly, on that note, remember, we know that this is going to be a feedback loop because it's biology, right? And biology is always full of these feedback loops. So they did this binding test with SEA to see how strongly it would bind to its receptor. And what they found was if they added some AEA to the mix, the AEA actually would directly compete with SEA for SEA to bind to its receptor. And so I just put this one last part of the map in this map, which is that the AEA is trying to prevent the binding of the SEA, which is, and the SEA is trying to activate the thing that's trying to break down the AEA by bringing it into the cell over here and then converting it harmlessly back to arachidonic acid and ethanolamide. Okay, guys, I know there was a lot of technical stuff. A lot of jargon. Hopefully that made some sense. I just wanted a quick summarize here. So the reason that I'm interested in SEA, I do sell it as a dietary supplement on the blog fireinabottle.net/shop if you'd like to try it out. The reason that I think that it's a very interesting controller is, one, if you watch my video, the history of body fat composition, stearic acid levels have dropped over the past 100 years. I think a very important question is one of the reasons that the obesity and diabetes epidemics have gotten worse is actually that SEA, that stearic acid signaling, has dropped along with the actual amounts of stearic acid in human adipose tissue. But what some of the data that I showed today made clear is that SEA is not equal to the other ethanolamide. It's controlled differently. It goes up and down at different times. It seems to have some inverse relationship with 2-AG. At least sometimes it does in the limited data that we have. I also showed that SEA, at least in glial cells, those are brain cells in mice, oppose the actions of an activated CB1 receptor, and showed that an overactive CB1 receptor we can say is causal in obesity in humans. And then lastly, I showed that as humans transition into diabetes, what you see is an increase in oleic acid levels and a decrease in stearic acid levels, and therefore presumably a drop in SEA levels, or at least you don't get the rise in SEA levels that you see in the other ethanolamides as people move from obesity or metabolic syndrome into diabetes. And I showed evidence that SEA and oleic acid have opposing effects on FAAH activity, which is the enzyme that breaks down AEA and OEA and the other ethanolamides. SEA speeds it up and, at least in certain tissues, helps clear the body of the endocannabinoids. Oleic acid slows that enzyme down and causes those endocannabinoids to build in the body. And that, I believe, is why the enzyme SCD1, which converts stearic acid to oleic acid, seems to have, it's one of the reasons why that enzyme seems to have such dramatic effects on metabolic rates, on obesity outcomes, etc. I hope you guys enjoyed watching. I'm going to try to keep the good content coming. I think I've got a pretty cool video planned for next week. So check it back out. I will see you guys soon.